Okay, we can begin. Okay, so next speaker of today is Professor José Espinosa from Madrid, and he's going to talk about applications of tunneling potential formalism.
Well, first of all, thank you very much for the invitation to give this talk in this seminar series, which is very interesting. So yes, I'm gonna tell you about this tunneling potential formalism that you probably don't know what it is. It's something, sorry. Yeah, okay. Yeah, it's something related to the decay of vacua in quantum field theory. So here is an outline of the talk. I'm gonna start reminding you what the usual way of dealing with this vacuum decays is using the Coleman's Euclidean formalism, and then I will introduce this new way of doing things, okay, which I call the tunneling potential approach. Before I continue, let me just tell you something that I forgot and it's important. Please interrupt whenever something is not clear. Just unmute yourself and ask the question, because I think it's better if we do it that way, okay? All right, so then this formalism is particularly useful when you include gravitational corrections. So in the second part, I will discuss those. First, reminding you how this is done in the Coleman-de Lucia way, and then how this works out using this new approach. And then I will go beyond Coleman-de Lucia. I will talk about two particular things beyond. One is pseudo-bounces. I will tell you what these are. And then, if time allows, some things about bubble of nothing decays, okay? So first, vacuum decay quantum theory. Why do you worry about this? So usually happens, for instance, if you work in beyond the standard model theories, that you end up living in a false vacuum that is not the true vacuum of the theory, and then you have to make sure that this vacuum is sufficiently long-lived. In fact, you don't even need to go to beyond the standard model physics. We believe that in the standard model, with the measure values of the top mass and the Higgs mass, we might be living already in a vacuum that is not stable. And then we have to worry about its lifetime. Then, as we heard in the previous talk, vacuum decay can also happen thermally by phase transitions in the early universe, and then you worry about this process too. It can also decay in the early universe during inflation, where the field can be kicked over the barrier by inflation. And then finally, if you worry about the vacuum landscape in string theory, then this process is crucial to be able to explain how these vacua are populated, okay? So let me start simple. This is just quantum field theory in 4 dimensions, 0 temperature, and you live with a scalar potential that looks like that, okay? So you are supposed to be living in this false vacuum here at phi plus, and if this were a classical theory, that would be a stable potential, but because the theory is quantum mechanical, this vacuum is not going to be stable, and it can, the decay can be triggered by quantum fluctuations that probe this deeper part of the potential. So this is a tunneling process between two states. The initial state is just the homogeneous false vacuum, phi plus here, and the end point of the tunneling is a configuration in which vacuum fluctuations have produced a bubble of this deeper part of the potential, where the field probes this deeper part. The energy of these two states is the same, is E equal to 0 if you normalize this to 0, and then you can tunnel between the two. And because this bubble nucleation can happen anywhere in a space, you are worried about calculating the rate for this process per unit volume, as I write here. And if the vacuum is sufficiently long-lived, then this is going to be exponentially suppressed. And you are interested in calculating this crucial quantity, the exponent for the tunneling. Basically, you can think of this quantity as the price you have to pay for constructing such a bubble. And you can think of this bubble as a semi-classical object. It's built of many quantum fluctuations, so it is expensive to build. And how expensive it is measured by this exponent here, okay? So as you can imagine, this is no problem. This was solved by Coleman in the late 70s. And the way he did it, he considered this tunneling decay as happening in imaginary time. So after rotating the Minkowski time to Euclidean time, you are ending up in a 4-dimensional Euclidean spacetime. And there you are interested in finding what is called a bounce. This is a field configuration that connects these two phases, the false vacuum and the bubble. Coleman also showed that this field configuration is O4 symmetric in this 4-dimensional Euclidean spacetime, and then it will just depend on the radial coordinate R, okay? This is going to be an extremal of the Euclidean action that I write here as this simple integral using the O4 symmetry of the solution. And notice that the potential has a positive term, and this is a signal that we are living in Euclidean spacetime rather than Minkowski. Okay. Now this bounce is an extremal of this action, and therefore is a solution of the Euler-Lagrange equation that I brought here. If you remember the previous talk, in the previous talk there was a 2 instead of a 3, and this is because this was done at finite temperature. And here I'm at 0 temperature. Okay. So the boundary conditions for this bounce are at the center of, yes? Was there a question? Okay.
Maybe not.
All right. So the boundary conditions are that at the center of the bounce, this field configuration is probing the deeper part of the potential. Remember this here somewhere. Then it has to be, it has to have a slope equal to 0 there. Otherwise, you will have a singularity coming from this term. And as you go away from the center of the bounce, then you have to fall slowly to the false vacuum 5 plus. Okay, so the profile will look something like that. Okay. So once you find this solution, then you can just plug it in the action, and the difference between the action for the bounce and the action for the false vacuum, this will give you the tunneling exponent that you are interested in calculating. Okay, so this is the standard way of solving this problem. All right. So now I want to present an alternative way of doing this calculation. Okay, so the alternative way, you consider paths that go out of the false vacuum beyond the barrier, ending at some endpoint, phi e. This path defines a function of the field, which I call tunneling potential. Okay, and to any such path, I will assign a number that is given by this functional that I wrote here. So it's just an integral in this field interval between phi plus and the endpoint of this quantity is basically the difference between the potential and the tunneling potential squared divided by the slope to the cube. Okay, and now the game is find the path that minimizes this action function. Okay, in varying the path, you will vary the shape and also the endpoint. Okay, until you find the minimum. And the claim is that the minimum that you will find by doing this is going to be precisely the tunneling exponent that you would calculate in the Euclidean formalism. I mean, you can prove this. Okay. And the path that minimizes this action functional will have an endpoint that corresponds precisely to the central value of the Euclidean bounce solution. Okay. Questions about this? Okay. So if everything is clear, I will just give you a possible derivation of this action function. Okay. There are several ways of deriving this equation that I brought here. I will give you one that is particularly appealing and simple. So in order to do this, I need a link between the tunneling potential formalism and the Euclidean formalism. And then you can show that this link is given by this formula here. So this is not the definition of the tunneling potential, but a link between the two formalisms. So the tunneling potential, which is a function of the field, is going to be exactly equal to this potential minus the gradient term expressed as a function of phi. This you can do if you know the bounce. You can calculate for every value of the field in the bounce, you can calculate what the slope is, and therefore you can write this as a function of phi. So if you do that, then you can check that this is going to be equal. These two things are going to be equal. Moreover, you can see that this quantity that I brought here on the Euclidean side is nothing else than minus the Euclidean energy. Remember that the potential has the Brown sign. So this is minus the Euclidean energy. So I will use this link between the two formalisms to prove the formula, and I will also use the thin wall action. Let me remind you what the thin wall action, how the thin wall action is derived. This applies whenever you have a potential like this, in which the two vacua are separated by a small energy difference, epsilon here, in which case the action can be calculated, the action for tunneling can be calculated semi-analytically and is given by this simple formula here. It depends on the energy difference, and the quantity is sigma, which is the wall tension, and is given by this integral that has a WKB flavor to it, okay? It's just the square root of the potential between the two vacua. You can rewrite this in terms of the gradient term, and this makes clear that this is nothing else than the gradient energy that you have per unit area inside in the wall. Okay. Now, using this link, you can rewrite this wall tension in the tunneling potential formalism is given by this integral, where here what appears is Vt rather than V plus. Okay, this is the formula in the tunneling potential formalism. So all you need to do for the next slide is going to remember this Euclidean energy link and this expression for the wall tension. Okay. So what I just reminded you was what is the action associated to a thin wall that separates these two vacua, which are close in energy. And this depends on the energy difference and the wall tension, and then the action is given by this. So what I want to do now is that I'm going to consider any wall, thin or thick, and I'm going to slice it in thin slices, okay? And I'm going to apply this formula to the thin slices and then sum over the whole slices, okay? So from the formula for the wall tension in the tunneling potential, for a wall tension that is the differential, because I'm considering a differential thin slice, I will just simply read what is the wall tension associated to this. Okay. From the fact that the Euclidean energy is minus the tunneling potential, the difference in Euclidean energy between these two sides of this thin slice is going to be nothing else than this expression, just from here. Okay. So I want to use these two differential wall tension and energy. I will plug it in here, and I will sum over all these thin slices. This is what I do here. I sum over the full family of slices. I use the thin wall formula, and there you go. You get exactly the action that I was writing before. Okay, quite simple. Questions about this? Okay. So if not, let me just remind you a few properties and applications of this tunneling potential formalism. So one nice property of this formalism is that this quantity that describes the tunneling, this tunneling potential, is on the same footing as the potential. It has the same dimensions. It talks directly to the potential. So you don't need to descend and calculate the field for the bounce. If you are interested in it, you can derive it from the tunneling potential, but sometimes it can be a distraction. You can get the full calculation just dealing with the tunneling potential. Okay. A nice property of this tunneling potential is that it is a monotonic function. As you go away from the false vacuum, this tunneling potential is going to decrease always. And this makes it easy to approximate numerically. Okay. Another nice property of this approach is that now the action functional, you have to minimize it. And this is in contrast with what happens in the Euclidean formalism. There, the bounce is not a minimum of the Euclidean action. Is a saddle point. And as you can imagine, it is much easier to find numerically a minimum than a saddle point. And this makes this formalism especially useful for numerics. And in particular, in difficult cases in which you cannot use the undershoot-overshoot method, like a multi-field case, the use of this tunneling potential method is going to be advantageous for these difficult calculations. And if you are interested in this, you can look up the details in this paper that I brought with Thomas Constantin. Okay, and this formalism that I described for you in 4 dimensions can be generalized to any dimension, in fact. And if you are interested in thermal phase transitions, then you can rewrite this action for 3 dimensions, which is the relevant number of dimensions for finite temperature, and then you can proceed as well. And just to connect with the previous question before in the previous talk, using this formalism, it is much easier to find the action than in the usual Coleman bounce solution. You don't need to use the undershoot-overshoot method, and it's usually in cases in which it's very difficult to find the bounce because you need really to tune the initial condition. This is much easier to do in this formalism. Okay. Questions about this? Because I'm going to move to gravity now.
Hello, Professor Espinosa. I had a question
Yes.
regarding this. Yeah, sir, Amindra. So I read your paper, both of them, one where it is generalized to the multi-field case, where while generalizing to the multi-field case, you did 3 different methods, as far as I can remember. The first one was expressing one of the fields in function as a function of the other field, and then take the path from the false vacuum to the true vacuum as a function of that, right? So, like when you are going from the false vacuum to the true vacuum, a path was needed, and that path was defined in terms of expressing phi1 in terms of phi2, or the other way around. and then you generalize it to the one field tunneling potentials that you had defined for a few cases.
Right.
Yeah.
So
yeah.
yes.
Please go ahead, sir. Go ahead, sir. Sorry.
No, just state your question. Right.
Yes, sir. So in that sense, what I wanted to know is in finite temperature cases, so that particular path, so while calculating, so actually I was trying it out. So while calculating that particular thing, the particular path becomes very important, because sometimes I cannot just take any functionality. So that particular path calculation becomes important in real cases, because it cannot be left arbitrary. So that is something I was curious about, and I wanted to ask you about.
Right. In the multi-field case, you will have to solve two problems, but this is generic. Also
Yes.
in Euclidean case, you have two problems. One is the path that will be followed in the field space, and another one in this formalism will be the shape of the tunneling potential. So you have to deal with these two things. So you have to probe different paths, and for each path, minimize a function. So it's a much harder problem than just with a single field, but you have to deal with these two parts of the problem. So in this sense, is also hard, as it is in the Euclidean case, but the fact that given a path, you can very fast calculate what is the minimum along this path. This is easier using this formalism. Okay, and moreover, if you are at finite temperature, then the path is going to change also with the temperature. Okay.
Yes, exactly, sir. That is what I wanted to ask, because then the false, like the true vacuum also changes with respect to temperature. So the path will also eventually change with respect to temperature.
Yeah. So everything will be a function of the temperature, and then you have to find at what temperature the tunneling rate is going to be maximum. Yeah.
Thank you, sir. Thank you.
Okay. More questions about this? So if not, I will move on to discussing gravitational corrections to this vacuum decay process. No? And then you might say, okay, I'm having a vacuum that is at the electroweak scale or TV scale. Why should I worry about gravity, right? And it's a relevant question. Now, the thing is, gravity will be relevant if any of these things happen. If the difference in the field between the two vacua is not much smaller than Planckian, or if the height of the barrier is not much smaller than Planckian size, or if the energy density in the force vacuum is not much smaller than Planckian. In any of these cases, then you have to worry about gravitational corrections. And before you say, okay, no, I'm at the electroweak scale, so I don't care about this, think twice, because in the standard model already, when the vacuum decays in the standard model, the jump in the field will be already of almost Planckian size. So already in the standard model, you have to include gravitational corrections if you want to calculate the rate accurately enough, okay? Anyways, whenever gravity is relevant, then you will need to include what is the reaction of the metric to the presence of the bounce, if you are doing it in the Euclidean way, okay? And moreover, besides causing some quantitative changes, gravity can also cause qualitative changes, and the two most important are the ones that I discussed here. So if you are tunneling out of a de Sitter vacua, due to gravity, now tunneling upwards is allowed, which you will never be able to do in the without gravity, okay? And in the case of anti-de Sitter or Minkowski vacua, a different thing happens is that gravity can forbid vacuum decay. So in potentials, in some kind of potentials, without gravity, you will always be able to tunnel to a deeper minimum. However, with gravity, it might be the case that you cannot decay even if there is a deeper vacuum, okay? And this is purely gravitation. So this problem was already solved in the Euclidean way also by Coleman and De Lucia in 1980. Here, things are very similar to what I presented without gravity, but now you have to assume O4. It hasn't been proven that the solution enjoys this symmetry, although it is quite likely that it will be. So people usually assume that this is the case. And then you have, again, to find the bounce, and you have to also worry about the metric, as I said. And thanks to this O4 symmetry, the problem is much simpler, and this metric just depends on a single function that I call here rho of r. So just looking at the Euclidean action that you want to extremize, then you can calculate, you can find the equations that these two guys have to satisfy. This is the equation for the bounce, and this is the equation for the metric function. Kappa here is 1 over m Planck squared, okay? But basically it's the same. You find these two functions, then you plug it in the action. For the bounce, you subtract the action for the false vacuum that carries its own metric, depending on whether it is de Sitter, anti-de Sitter, or Minkowski. And the difference between the two is going to give you the tunneling action that suppresses the decay. Okay, so this is the usual way that you would go about it. And now, can you generalize the tunneling potential to this case? You can. And it's exactly the same kind of game. So you again find these paths out of the force vacuum, but now the action density that you use is different. It includes gravitational corrections. It looks like this, where this d function here is defined here. It's just basically like a gravitationally corrected slope for the tunneling potential. Okay. So, of course, if you take the kappa equal to 0 limit of this thing, then you will recover the action for zero gravity case, the one that I gave you before. And by minimizing this action, you will get exactly the same result that you get in the Euclidean formalism. Okay. One noticeable difference between this way of doing things is that here you don't need to deal with two functions. In the Euclidean case, you have to find the bounce and the metric function. Here is just the tunneling potential that you have to find. Okay. Okay, so one nice thing about this formalism is that the formula that I wrote for the action is universal, meaning that it is valid for anti-de Sitter, Minkowski, or de Sitter. It's exactly the same formula. What is different between these two cases is that in Minkowski or anti-de Sitter, the form of the tunneling potential is still monotonically decreasing as you go out from the force vacuum, as shown here. While in de Sitter, things are more interesting. First, the tunneling potential goes being equal to the potential, and then at some point it goes up and down below the barrier, okay? And it does something like this. So it's not monotonic in this case. So the solution has two different regimes. One is what I like to call Hawking-Moss interval, and the reason for calling this will become clear later. And this is the Coleman-de Lucia regime or interval. And this is because if you solve this problem of the decay of this de Sitter force vacuum in the Euclidean formalism, this would be the field range that will be covered by the Euclidean bounce. Okay. Now the fact that you have this kind of shape has a very nice thermal interpretation that you can find in this paper here. Okay. So it is well known, coming back to Hawking and Moss, it is well known that in the de Sitter case, if the energy density of the force vacuum is large enough, then the Coleman-de Lucia bounce at some point disappears. There is no decay by Coleman-de Lucia bounce. Okay. The vacuum is still unstable and can decay, but it does so via different instanton, which is the so-called Hawking-Moss instanton. This is an instanton in which the full region inside your horizon will transform from the force vacuum to a value that is at the top of the barrier that you are tunneling below which, okay? And the action for this decay via Hawking-Moss is different. It's just given by this simple formula that just depends on the energy densities in the force vacuum and at the top of the barrier, okay? So in the tunneling potential formalism, without the Coleman-de Lucia interval, everything happens in a very simple way. There is only this Hawking-Moss interval from phi plus to the top. And if you plug in the formula for the action that I wrote, Vt equal to the potential, as it happens here, then you will find that this integral can be solved exactly, and what you get is precisely the Hawking-Moss rate, okay? Which is a nice property. You don't need to modify your action to take into account this phenomenon. It comes out automatically, okay? So let me just discuss now the other interesting thing that happens with gravity is the gravitational quenching of decay. This can happen in anti-de Sitter or Minkowski decays when the energy density is 0 or negative. And in some potential gravitational quenching of the decay, it happens. And in this formalism of the tunneling potential, this comes about because this quantity d that is defined via this square root has to be real for the vacuum to decay, right? Now, in the case of anti-de Sitter and Minkowski, inside the integral, you have a positive term, which is the square of the slope, and then you have a term that is negative because the tunneling potential is negative. So you have to make sure that these two sum to a positive thing. Otherwise, decay will not be able to happen. This means that the slope of the tunneling potential has to be large enough. How large? It has to be larger than the value for which this is equal to 0 that I wrote here. Okay, so this is this critical value of the slope, and the slope of the tunneling potential has to be bigger than that. So you can solve this equation with a negative sign of the slope, just leaving from the force vacuum, and this will give you a solution that I call critical tunneling potential. Okay, this corresponds to a D equals 0 solution. And this formula here tells us that the tunneling potential, because the slope is bigger, has to lie below this critical thing. Okay. And notice that the slope of this critical tunneling potential is proportional to kappa, and this means that if the gravitational effects are strong, this dash curve will be very much curved. If gravitational corrections are small, which means like kappa can be considered small, then this will be not so much curved down. Okay, so let me show you this kind of two limits. In the weak gravity limit, this is very slightly curved, and then there is plenty of room for the tunneling potential to decay. And in this case, the tunneling decay will not be forbidden. Okay. However, if you are in a case in which gravitational effects are strong and this is very much curved, it might happen that this does not touch the potential. And because the tunneling potential has to lie below this line, there is no way you can go from here to that part of the potential without crossing the line. This means that there is no path that will give you a D that is real, and this means that there is no possibility of decay of this false vacuum, even though there is a deeper vacuum there. So basically what is happening here is that there is no possible decay in the sense that there is no possible field configuration to which you could decay. This means that you can try to build a bubble with the same energy as the initial state, but any bubble that any field configuration that you build will have a positive energy, while the initial false vacuum has zero energy. So there is no possibility of tunneling between these two states. And this means that there is a positive energy theorem that you can formulate for these kind of theories. Okay. So to get a better understanding of this phenomenon, let me just do the following argument. So suppose you have no gravity and you are in a situation in which tunneling is very much suppressed because the energy difference between the two vacua is very small. Okay. So this epsilon is very small and it's very hard to tunnel, but you can always tunnel. And the reason is that you can always form a bubble with zero energy to which you can tunnel from this false vacuum. And the reason that you can always do it is the fact that the energy inside the bubble that you gain grows like r to the cube. It's proportional to the volume inside the bubble, while the positive energy in the wall tension is only growing like r squared. Okay, this means that there is always a solution for this equation, and there's always a bubble large enough that will give you E equal to 0. Yeah. With gravity, things are different because inside the bubble, now the space is anti de Sitter and it's a curved space. And then the scaling of the volume inside this bubble does not scale like r cubed, it scales only as r squared. A nice mnemonic of this fact is can be understood that using this Escher engraving. This is in 2 dimensions. You can think of it in 3 if you want. What this negatively curved space shows with this nice engraving is that most of the volume, you can think of these angels and demons as having the same area. Okay, so you see that most of the volume is going to be near the surface, near the bubble wall. Okay, and this explains why the scaling of this volume in this negatively curved spacetime is only growing like r squared. And this means that if the potential has some properties, then it might happen that there is no solution for this being equal to 0, and it is not guaranteed that you're going to find always a field configuration, a bubble field configuration to which you can tunnel. Okay. So between these two cases that I showed you before, between the weak gravity and strong gravity, there is a limiting case in which this critical tunneling potential goes from one vacuum exactly to the other. Okay, this field configuration corresponds to a case in which this square root is equal to 0 exactly. This means if you look at the action for this object, that the action is infinite, so there is no decay still, but this has some physical meaning. This corresponds to a domain wall solution that is interpolating between these two vacua. Okay. This cannot happen for every potentials. The potentials for which you could have this kind of flat domain wall between the minima, they have to have a form that you can derive actually from d equal to 0, just solving for the potential. And then you can derive that the generic form that these potentials, these critical potentials have, has to take this form, okay? And this is a rederivation of a result that it was long known in the mid-80s, okay, it was derived. But there is a very simple derivation that you can find from here, just by solving this d equal to 0 condition, okay? So now I will just move beyond Coleman-de Lucha. So if you have questions about this Coleman-de Lucha alternative, now you can ask if you want. Okay, so if not, what I'm going to do now is I'm going to try to find solutions for the Euler-Lagrange equation that you can derive for Vt. If you just vary the action that I wrote for Vt, you end up with a Euler-Lagrange equation that looks something like this. Okay, so instead of using undershoot overshoot as is usually done in Coleman's approach, what I'm going to do is I'm going to find a family of solutions without doing any tuning. Just I will keep all the solutions as valid solutions. Okay, and I'm going to do this in a de Sitter case. You can do the same in anti-de Sitter. In de Sitter, as we know, first the tunneling potential goes up and then goes under the barrier. So I'm going to use as an initial condition to solve this equation, this initial value, phi sub I initial, that I will vary all along this slope. And I will have a look at the solutions that I find. The boundary conditions that I will use then is that the tunneling potential at this initial point is equal to the potential, and the slope is smaller, is given by 3/4 as dictated by this equation. Okay. Among these solutions, of course, I will find the Coleman-de Lucha one. And if you are looking for it, you will require some tuning of the initial condition. But because I'm interested in seeing what kind of other solutions I get, I will just vary this initial field value and see what I get. Okay. So this is shown in one particular example. So you vary this initial value and then you get these different solutions. In red, I show the Coleman-de Lucha one. You can see it here in this zoom out version. On top of it, you find these solutions in green that I will call pseudo-bounces. You have the trivial one, which is the Hawking-Moss one, because this is a de Sitter case, you have also this one. And below Coleman and de Lucha, you find some interesting solutions that go all the way to minus infinity, okay? That seems peculiar, but you will see that there is a physical interpretation even for these kind of solutions, okay? This will turn out to be relevant for the bubble of nothing decays. And it will be relevant if this field that I'm using here is just a size modulus and describes the size of an extra dimension, okay? So interestingly, these solutions have finite action. You can just calculate the action using the action functional that I gave. And then what you find is that you find, depending on the initial value that parameterizes this family, you find Coleman-de Lucha as the minimum in this branch. You have Hawking-Moss that has a higher action, and the pseudo-bounces connect these two solutions, okay? And then bubble of nothing solutions have this funny shape. And, oops, sorry. And in some cases, they are going to be the dominant decay modes, okay? Because they are lower than anything else. So let me just explain what these pseudo-bounces are. So these are solutions that minimize the action functional if you hold fixed the endpoint. This is not what you do when you are looking for Coleman-de Lucha, because when you look for Coleman-de Lucha, you look for the absolute minimum, and you have to leave this endpoint free, okay? But if you hold it fixed, then the solution that you will find for this, for minimizing this action with this hold fixed, this is going to be a pseudo-bounce. Because what you are doing is not minimizing the full action. This means that they are not true extremals of the action. In particular, the action will vary if you vary the endpoint, of course. However, even if they are not true extremals, there are at least two cases in which they can become relevant. For instance, if the variation of the action as you vary the endpoint is small, This means that you are in a situation like this, in which the minimum of the action corresponds to Coleman de Lucia, and then the nearby field configurations, which are pseudo-bounces, they have an action that is not much bigger than Coleman de Lucia. This means that you can still decay by forming these field configurations, and the price you have to pay is not much more expensive than Coleman de Lucia. This means that if you want to calculate in a situation like this what is the rate, you have to also sum over all these configurations which are not Coleman de Lucia. Okay. Now, in other cases, what happens is that there is no bounce at all. So the potential is such that the minimum of this action as a function of the endpoint, the minimum occurs only asymptotically when the endpoint goes to infinity. So this means that you can prove it in some potential that there is no bounce at all. However, the vacuum can still decay. And because of this kind of shape that the action has, you also have to integrate over all this flat direction here. Okay? So, in a sense, these pseudo-bounces are objects which are very similar to what people call constrained instantons. These constrained instantons, if you're not familiar with them, these were the kind of forcing a theory that has no bounds to modify the action in such a way that you force the theory to have a bounce. And this you do as a way of trying to approximate what the real situation for the decay is. Okay? What I'm showing you here is that these pseudo-bounces are the best constrained instantons you can think of. And to explain this, let me give you this example. This is from some decay of some particular potential. What you have here is the endpoint of possible decay configurations. And this other axis is the different parameter that is making you explore different field configurations also. The field configuration space is multidimensional. I'm just taking two dimensions in this multi-configuration space. And what I'm plotting is the action as a function of these two parameters in field space. Okay. What I show here is that for a fixed value of the endpoint, by definition, the minimum, if you cut this in slices, the minimum of this action is going to be the pseudo-bounces by construction. And what I'm showing here in red is possible constraint instanton that other people were using in order to get a solution for this kind of potential that had no bounds. Okay, so what you see here is that the pseudo-bounce is going to beat always other constraint instantons because it guarantees you that you are tracking the bottom of the potential value like this. Okay, so in a sense, these are the best constraint instantons that you can think of. This is all I wanted to say about pseudo-bounces. So if you have questions, please, this is the time to ask about them. Okay. So if there are no questions on this, I will just move on to bubbles of nothing. Okay. So what are these? These are decays, a new kind of decay of spacetimes which have a compactified dimension, like, for instance, 5-dimensional Kaluza-Klein. This was discovered by Witten in 1982. So 5-dimensional Kaluza-Klein is nothing but Minkowski spacetime times a circle. So this means that at each point in a space, there is an extra dimension that is compactified in a circle. I'm representing this just showing one extended dimension. You have to think of 3 instead of 1, but just to picture this, just one extended dimension and the compact dimension parameterized by this angle theta with a radius which is r. This is the Kaluza-Klein radius. Okay. What Witten showed was that this spacetime is unstable. It is unstable to decay towards this other configuration in which what you have like a region in a space that with radius curly r here. This is like a bubble. And as you approach this bubble, the surface of this bubble, the size of the extra dimension is shrinking smoothly to 0, as shown here. Okay. In principle, the radius of this bubble is different from the Kaluza-Klein radius, although in this simple case, they will turn out to be the same, but in general, they can be different quantities. Anyway, this process, which is a quantum mechanical tunneling process, is described by a Euclidean instanton, as usual. Now, the thing that you only have gravity here. There is no scalar fields around. So this is described by a Euclidean instanton that is purely gravitational. Okay. The form of this gravitational instanton is written here. This is the Witten bubble of nothing instanton. If you think of it, it's just like a Euclidean version of a Schwarzschild metric. Okay. In particular, you can see here that the radius of the extra dimension goes to 0 as this distance r approaches the Kaluza-Klein radius. Okay, so indeed the radius of this bubble of nothing is equal to the Kaluza-Klein radius. Okay, you can also calculate what is the Euclidean action associated to this tunneling, and it's a finite quantity given simply by this combination of the Kaluza-Klein radius and the Planck scale. So there is a finite probability that the vacuum decays in this way. So what you're finding here is a very weird kind of bubble, in the sense that in the previous bubbles that I was describing before, you always had a potential with two minima, and inside the bubble that you form, there was a phase of the field that is probing the deeper part of the potential. But this bubble of nothing object is a very different object, in the sense that inside these bubbles of nothing, there is no space-time, okay? It's not a different phase, there is no space-time. Space-time just curves smoothly there, and there is nothing else inside, okay? So this very spooky thing, if you create it, it will start growing as the usual bubbles do and will destroy your space, okay? It's a smooth configuration, there is no singularities, and the curvature is not large, but it will just kill the space-time, okay? So why people worry about this? Well, of course, they are relevant for populating the stream vacuum landscape. It is believed, in fact, that this decay channel is responsible for the decay of non-supersymmetric vacua in string compactifications. And don't ask me about this because I'm not an expert, but I understand that it's also relevant for what people call a cobordism conjecture, which is very much in fashion. So interestingly, there is a four-dimensional point of view to understand this bubble of nothings. What you do there is just, instead of living in 5 dimensions, you go to an effective theory in 4 dimensions, in which you include a scalar field, a geometric modulus, that is going to track what is the size of the extra dimension, okay? So the link between this field phi and the size of the extra dimension is written in here. This is the radius of the circle that is given in 5 dimensions by this simple formula. And in 4 dimensions, you just parameterize this in terms of this phi. Okay. So as you approach the core of the bubble of nothing, which is when r goes to r and this shrinks to 0, this corresponds to phi going to infinity. So this is going to be the center of the BOM. Okay. When you take the false vacuum, this corresponds to the radius going to infinity. As usual, when you go away from the instanton, you are in the false vacuum. And just using this relation, then you find that this corresponds to phi going to 0. Okay. So when you describe this decay using this phi field, then the decay will be like a decay from 0 to infinity using this language. Okay. The bubble of nothing instanton metric, you can rewrite in a form that is the same for the Coleman-de-Lucia. Okay. Just doing a change of variables between the initial 5-dimensional radius r and this new psi variable. And this change of variables sends this surface of the BON into psi equal to 0, okay? So by doing all this, what you are doing is reducing the bubble of nothing decay to a Coleman-de-Lucia problem, okay, with a field that will tunnel and a metric, okay? But it's a special one in the sense that it is singular. At the center of the bounce, now the field will go to infinity, like here. And instead of having 0 slope, now because you have to reach this infinity in a finite range of psi, this slope has to go to minus infinity. When you go away from the center of the bounce, then you fall into the false vacuum as usual. And by doing this in 4 dimensions, then you can show that by using this Coleman-de-Lucia approach, you will also recover the 5-dimensional action of Witten. But in order to get the right value, you have to be careful, and then you have to keep some boundary term that comes from 5 dimensions. You keep it, and then you can reproduce exactly the same result. Okay? So in a nutshell, what you're doing here in 5 dimensions, this is the shape of the instanton that you're trying to calculate. And in 4 dimensions, this corresponds to this field profile going from 0 to infinity. Okay. Now, this four-dimensional approach is very useful to study what happens to the bubbles of nothing when you stabilize this extra dimension and when you introduce a potential. In the case of Witten, there was no potential, so it was not a very realistic scenario. And in more realistic scenarios, you have to stabilize this radion field. In any case, because this allows for a Coleman-de Lucia description, you can also use the tunneling potential description for it. All right. So let me show you how this looks like for the Witten case in which there is no potential. So you can derive that the tunneling potential for describing this bubble of nothing decay is just given by this simple formula, like a cube hyperbolic sinus. Okay. So it goes like this, from phi equal to 0 all the way to minus infinity, and it goes exponentially fast there. Okay. So in a sense, this you can think in this language, you can think of the bubbles of nothing as tunneling from some vacuum to minus infinity anti-de Sitter spacetime. Okay. A nice property of this tunneling potential approach is that if you plug this in the action that I showed you all the time, you will reproduce exactly the same result as Witten, and there is no need to add any boundary terms. So it's automatically giving the right result. Okay. So as I said, for realistic scenarios, you have to fix what is the value of the field of the radion field, and this fixes what is the size of the extra dimension. Now the question is, for what kind of potentials you can still have a bubble of nothing, and for which you will not have. Okay. So the sources of potentials for the radion field are several. Some of them want the dimension to decompactify. Others want the dimension to shrink, and then if you combine them, you can get potentials that will achieve what you want, just to find a minimum for this potential that fixes the radius of the Kalusak line space. Okay. So what we did was using this tunneling potential formalism, in particular, just looking at the asymptotics of this Euler-Lagrange equation for the tunneling potential. In this particular case, when we are interested in fields that go all the way to infinity to describe bubble of nothing decays. And so we were able to classify what kind of potentials will allow for bubble of nothing decays, what kind of tunneling potentials you will get. And you can also address the question of when is this channel, this bubble of nothing decays, the dominant decay? Well, it is not. I will skip the details. I will show you just these 4 different types. This is the potential and the tunneling potential, which is always going exponentially to minus infinity. You can have bubbles of nothing even with potentials which look perfectly stable, that go exponentially to positive values, and still it is possible to find bubble of nothing decays. Okay. So let me just, I don't know how I'm doing with time. How much time do I have left?
We still have 10-15 minutes. If
10-15 minutes, okay.
Yeah,
So
if you want, we can extend it.
All right. So let me just give you one example of this thing, okay? So I'm going to take Witten's example, but I'm going to use the non-zero potential. I'm going to introduce the non-zero potential for the radion field. So the potential will look something like this. It's Minkowski, and then has a deeper minimum somewhere, okay? Just using this study of the asymptotics when phi goes to infinity, we can derive, just looking at the equation of motion for the tunneling potential, that it will go to minus infinity exponentially with some coefficient here. And the d function that enters into the action will have also an exponential decay row with a different coefficient here. Now, these 2 prefactors depend on a free parameter A. This free parameter is the free parameter that is parameterized in this family of solutions. Remember, when I showed you the de Sitter case, there was a full family of solution. The same happens for these BON solutions when you decay from Minkowski. This A is simply labeling this family, okay? Now, as a function of this label, then you can plot what you get for this particular potential. You get the prefactor for the tunneling potential here, and this prefactor for the D function here. And the other curve is just showing you what is the action associated to these BON solutions, okay? So you need, in order to get further, you need some 5-dimensional input, because depending on what is the radius of your extra dimension, you will end up with a different value of this coefficient, okay? And depending on what is the size of the BON radius, you will get a different coefficient D. So once you fix the radius of your theory, then this fixes VTA, and then you can use this plot just to show which two solutions that you have. Okay, for this particular value of VTA, you will have two solutions, A and B. And this will select in the family of solutions, these two here. Now, which one will be preferred? Well, you can read immediately what is the action associated to them, and this is lower. This means that this will be the one that will describe the decay of this vacuum for this particular choice of Kaluza-Klein radius, okay? And this other function that is related to the radius of the bubble of nothing will tell you immediately what is the size of this bubble of nothing. So everything, all the information that you need is encapsulated in this plot here. Another interesting thing is that if you choose the radius of your Kaluza-Klein in such a way that the prediction for this parameter lies below this minimum, then there will be no solution. And this means that for that particular choice of Kaluza-Klein radius, there will be no BON decay. And you can also describe this using this formalism, okay? So this was just an example. You can do many more things. If you are interested, I will just point you to the paper that we wrote. It's a long paper with a lot of cases and discussions. But basically, this is how it works, okay? And with this, I get already to my conclusions. So the main hope of the talk is just to convince you that this tunneling potential formalism is simple and useful. For that, I use these four things. First, to describe vacuum decay, that you can also do for finite temperature transitions. Then it's particularly useful to describing gravitational effects in vacuum decays. And then beyond the usual Coleman-de ones, I discuss these pseudo-bounces, which are alternative decay modes that might be relevant in some cases, and then bubble of nothing decays. There are other applications that I did not mention. Some are already finished, some are in progress. You can use this to describe the formation of cuboids, to discuss the positive energy theorems in anti-de Sitter maxima when you are interested in the decay not of a minimum anti-de Sitter minimum, but an anti-de Sitter maximum. For describing flat or curved domain walls with gravity, and also for standard decays, not the BOM ones, but the standard ones when you have extra dimensions also. And in general, the message would be that whenever you have a problem in which Euclidean solutions are relevant, it might be worth checking if this new formulation that has no Euclidean quantities in it is useful for the description of your problem. In some cases, it might not be, but in many other cases, as we have found several times, it is really, really simpler in this way, okay? And just the final slide, let me just give you this, this slide, which is summarizing the results that I wrote in a proceedings paper that I wrote a couple of months ago. So it's called the unreasonable effectiveness of the tunneling potential in the following sense. It's always nice to have an alternative way of calculating things, as this is with respect to Coleman's way. And what I find intriguing is that this way of doing things has a number of unexpected properties that we had no right to expect, but nevertheless they happen. One is the fact that the new action that you have to extremize, you really have to minimize it. There was no reason for this to happen, but it's a nice thing that happens. Another nice thing that happens for no reason is that this action form is universal. It is valid for any value of the energy density, and in particular for the Sitter, it immediately reproduces Hawking most without the need of modifying it. It could have been the case, okay? It's also interesting that you find new solutions beyond Coleman-de in a natural way. I try to show you this in the way I presented pseudo-bounces and bubble of nothing. You just solve the equation and out they come these solutions that are begging for a physical interpretation because they have a finite action, and indeed they do have a physical interpretation. And it's very natural to find them in this formalism, okay? And finally, the fact that I already told you about for bubble of nothings, that there was no need of modifying the action, including extra boundary terms to get the right result, is not only in bubble of nothing decays that happens, it also happens when you are interested in calculating the decays of anti-de Sitter maxima. In the usual case, doing it in the Euclidean formalism, you need to include boundary terms to make sense of the whole problem. And here, You can apply the same kind of formalism and the same action will give you the right result in a very simple way. So what does it mean? Does all this mean that there is a more fundamental origin for this object, this tunneling potential and this action? So the answer is I have no idea. I don't know, I cannot think of any more fundamental origin for this object, but nevertheless, all these nice properties make this a question that I think is worth asking oneself, but unfortunately I have no answer to it. And with this, I will just stop. Thank you.
Okay, thank you for the nice talk and a very excellent overview of the topic. Any question from the audience, please unmute yourself and ask. Okay, I have a couple of things to ask.
Yep.
One of the things I was wondering is that this method seems to work with different kind of potentials and interactions that you showed, right?
Yeah.
But still at the level of expansion, it is still, so does it still assume weak perturbation theory, like my couplings needs to be less than 4 pi or something like that?
Well, in exactly the same way as you would have in the Euclidean case, one is using the semi-classical approximation. Okay,
Mm-hmm.
And this means two things. One thing is that the action has to be large enough, otherwise you cannot trust the calculation.
Mm-hmm.
And because the action, this is a non-perturbative effect, and the dependence of the action on the couplings is inversely proportional to the couplings. It's like whenever you are in the semi-classical approximation, then your couplings have to be small.
Mm-hmm.
All right. So it's kind of built in the fact that you can calculate this action at all is related to the fact that you are in weak coupling.
Okay. So
if you are in strong coupling, it might happen that the action, typically what's going to happen is that the action is going to be small, and then there is no reliable method of calculating it anyway.
Okay.
But sorry, and then usually you are not interested in these cases, because if you are living in a vacuum that is really decaying very fast, then you typically are not interested in those cases.
But for example, if I have a very strongly coupled theory, let's say I have a QCD, dark QCD like theories, right? So then my couplings can be quite large, and then I probably I don't know how to do the radiative corrections to my coupling, right? So
So if there is no alternative weak coupling expansion, I don't think you will be able to use this thing.
Okay. But is it not possible to extend this formalism, for example, using functional group renormation methods?
I have no idea. I haven't thought about this at all, actually. So I really don't know. Sorry.
Okay. And the second question which I wanted to ask you is a bit more phenomenological question. So apart from having, let's say, apart from having the standard gravity, which is a Coleman-de bounce, have you considered the possibility of having some impurities in the vacuum, in the false vacuum, for example, presence of some primordial black holes, or say some presence of some cosmic strings or something which can induce a faster decays?
But in principle, you could try to modify the formalism in order to do that. I was meaning to have a look at it until I started seeing results that were pointing towards the fact that probably there used to be the idea that these primordial black holes could trigger much faster decay, but then it started to become more or less clear that this is not going to happen. And then I was not so interested in looking at it. But in principle, I guess one could modify the formalism to take that into account. Yeah.
But is it true that presence of primordial black hole does not make the vacuum decay fast? Because I think when you have a presence of primordial black hole, it is just more than just having an impurity, because the temperature profile also changes around the primordial black hole.
Yeah, I'm thinking of a paper by Strumian,
Yeah, but
if
yeah,
I do not,
and yes,
yep.
yes, I know that paper, but then people have written another paper which came out a few months ago, and they showed there were some approximations in the paper by Alessandro, where the temperature profile around the primordial black hole was not considered. So if you have a primordial black hole, it's not just a primordial black hole, but because of presence of Hawking evaporation, along with it, the temperature profile along the primordial black hole gets slightly modified, and that makes the vacuum decay faster. I can send you the reference.
Okay, yes, please. Yeah,
Sure.
then maybe I should have a look at it. Thank
Sure.
you.
And I think this paper also got recently accepted in PPRL as well.
I see. Okay,
But my question was actually more general than primordial black holes. You can also imagine other kind of impurities, like you could imagine having, for example, cosmic strings in the false vacuum, or you can imagine having the domain walls. So could we have like a generic way of understanding how presence of impurities could impact the false vacuum tunneling, whether it could be made larger or not?
You mean using this method, right?
Yeah.
Yeah. So one of the things that goes into this, in the simplicity of this method, is the fact that you have an O4 symmetry. Okay.
Oh, I see.
And then if you break it, then it's going to be more complicated, and I have no idea really how more complicated it's going to be. So if I look into it, I will be able to answer in more detail the question. But
sure. So I think that there are very old papers by Weinberg and the Texas Working Group from the 1980s. Then they considered very simple cases where you have a cosmic string and how they could induce electroweak vacuum decay. If you have a dominant wall, how they could induce. I mean, these are very old calculations, of course.
Right, but then you lose the O4 symmetry, right? Because of the presence
for
of
the cosmic strings, probably.
Yeah.
But in some cases you don't. Okay, right now I don't remember.
So if you have like a point light thing, like a black hole and things like that, yeah.
So yeah.
So it's worth then looking at it. I will try to.
I can also send you the old papers from which I have.
Very good.
Okay. Any other question from the audience? Please unmute yourself and ask. Okay, if not, then one last question, which I was wondering. So apart from having the Coleman-de bounce, which takes into account the presence of Einstein-Hilbert term, could I also not have other kinds of interactions with gravity? For example, non-minimal coupling of the scalar gravity, or even R square or R mu nu kind of terms had derivatives in R, and
Yes, you could, and then you can modify the approach. I didn't try with R squared, but I did try with a non-minimal coupling, and also with a non-trivial kinetic term in which you have some field dependence multiplying the kinetic term for the scalar field. Okay, so you will have just the potential, then the non-minimal kinetic term, and the non-minimal coupling to gravity, to R. And then you can generalize the whole thing. And what happens is that the action density that you have will be a function of all these three functions, but this can be done. Okay. And the game will be the same, just minimizing this action function.
Yes. The reason I'm asking you is because, as you know, the Einstein-Hilbert action is a non-renormalizable theory. But if you introduce R squared and R mu nu squared with particular coefficients, long time ago Stelle showed that this becomes a renormalizable in the UV, and then with particular predictions of the coefficient, because these coefficients also undergoes RG correction. So they're not constant, the non-minimal coupling or the coefficient of the R square or the coefficient of the R mu nu square. So it might be interesting to see what happens to the vacuum decay in presence of a renormalizable theory of gravity.
So I'm sure this can be done. Yeah.
I see. Okay.
But I haven't done it. Yeah.
Okay. Thank you for.
You're welcome.
Any other questions from the audience? Okay, if not, let's thank the speaker and thank
you. Thank you for the invitation.
Again for the nice talk. Will you be able to send us the slides?
Yes, sir. Of course, I will do right away.